as you're coming in, I'm going to ask you to do something for me that we're going to need. It'll make things easier. I would like the professor/teachers to seat themselves over here. I would like the clinicians who also teach to sort of sit centrally. And I would like the clinician docs who are primarily in the clinic with patients and not teaching over here.
Haven't accounted for 17 of the participants.
Okay. Folks who aren't running classrooms over here with the clinician docs. Okay? If you're not in a formal teaching role over here. If you teach, you don't have to be a professor at a college, but if you teach in some capacity, over on that side. Okay? All right, so you guys are at the first, to the best of our knowledge, the first continuing medical education course on evolutionary medicine. You are our ambassadors to the world, like it or not. You're going to go home, you're going to teach. Some of you are already teaching evolution and evolutionary medicine sorts of things. Other ones, if you deal with patients, deal with other professionals, and you're still going to be spreading information about these topics. And we want that to be done well. We hope that you want to do that well also. One of the things that's very popular in the pedagogical literature in recent years is the concept that students learn best. Anybody really learns best, you know, formal student relationship or not. Anybody learns best when they do something, right? Not when you just stand and listen to, you know, talk, and you memorize. That's not the best way to learn. You learn best when you actually do something. So evolutionary topics and evolutionary topics related to health are really easy to connect to the real life, real experience, real cultural setting of the people that are learning, right? Because it's about us, it's about humans, it's about how our genes interact with our environments and our behavior and produce health outcomes and why it works the way it does. Well, everybody has a real life, a culture, a set of behaviors, an environment, right? They can think about themselves, the people around them, their culture, their habits, and come to conclusions. And once you connect that back to theory, they own it. They've got it. It's theirs for life. It's not a memorized factoid that's just going to dissolve, okay? So we're going to use that to try to maximize teaching and learning. It's active, not passive. It's concrete, not abstract. It's real, not just theoretical. But then we can bring it back and tie it to the theory. Okay? So I'm going to give you a couple examples very quickly, and then you're actually going to design some projects, exercises, tasks that you can use in your classes and that you can use when you talk to people about these ideas that'll help them get the idea better than they would otherwise. Okay? So I'm going to show you an example. I teach about kin selection a lot. I use it when I talk to my classes. So students always, when we get to those kinds of issues, say, but wait a minute, how can organisms behave with respect to how closely related they are to other organisms if you don't know the theory, right? I mean, I didn't know the theory of kin selection years ago, but presumably I was still preferring and doing more altruistic behavior toward certain relatives than I was toward strangers. So how did I do that, right? I mean, there's some algorithm in your head that lets you do it. So before I ever introduce the topic, I give my students this one-page, very quick exercise for them to do. I say, imagine that you're creating your last will and testament, and you have $100 million, okay, just to make it simple. You can give away your $100 million in chunks of $1 million packets, okay, just, again, to make it a little bit simple. So you have 100 shares of $1 million that you can do anything you want with. Tell me what you're going to do, okay? Who are you going to give it to? What's the relationship to you by which I say to them, you know, is it your sister, your mother, a friend, a stranger, a charity, you know, what, like, who is this so that I know, and how many shares are you going to give them, okay? You don't have to put your name on it, just hand it back to me. So I collect these things all up, and I go back to my office, and I dump it into an Excel spreadsheet, and where's my mouse? I do that. I sort it out by, I take the relationships they give me, right, put them into categories in the spreadsheet, and I compute a graph like this that shows how closely related the individual they're giving it to is and how much they're giving. And I do an average across the students for the class, and we see that students actually give more to individuals who are related to them by half than to those who are related to them by a quarter, more than to those who are related by an eighth. And then we have this funny thing where it's complete strangers and charities and things like that, okay? So the point is not that this falls out perfectly with respect to the predictions of kin selection. That's not the point. The point is this is them. This is their data. And when we put this up, I say, wow, so there's some things that are suggestive that, like, somehow you kind of knew this or you behaved in accordance with it, even if it wasn't conscious. We talk about the peculiarities of these things, and then we say, and so what's going on with this over here? Does that make sense? Does it not make sense? Does the fact that most of them are 18 years old have anything to do with who they're giving money to because they don't have children, most of them? So we have that discussion. And by the time we're done, they own this material. It's theirs for life, and they get it, right? In a much different way than if I stood there and said, so we can compute these degrees of relatedness and blah, 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 and they're still, yeah, theoretically you could do that. This is them, okay? So they get it. Let me give you another brief example. I make my students, we talk a lot about, in a very general way in one of the real low-level classes, about the changes in diet, right? The whole concept that our diet just isn't the same as what we used to eat during the Paleolithic, right? And this can be kind of dry material for students, right? We get more of this nutrient, less of that nutrient. How did we get this nutrient? How do we get that nutrient now? I mean, that can be pretty dry, right? So what I do is, these are going to be posted, by the way. You're not going to see this whole thing. This is like an 18-page document because it's what they get as their exercise packet to work in. I make them keep a food log for a week. They have to write down everything they eat in a food calendar, diary. They have to go in and tabulate the nutrient content of all of those food items, total it up, average it for the week. At the end of it, I give them a table of a paper that's in the professional literature from Boyd Eaton's work, what we think the Paleolithic nutrient components of diets might have been like, and I say, put your numbers next to it. What do you look like? Okay? And then we say, so what could be the importance of the fact that we get more sodium than potassium, and that is completely bizarre, right? That other organisms don't behave that way. There's a huge switch in our diets. It's a big problem. So we can then delve into specific items as we need and as we want, but it's their information, right? Now, I didn't realize at the time that I designed this was just to get them to buy in and think about what they're doing, but it actually turns out that, some people say, well, they're just going to make it up. They're not really going to write this down every day, but it's still a win-win. What are they going to make up, even if they're making it up? They're going to make up what they think that I want to hear, what they think is the right thing to do with their diet, right? If they change their diet because I'm asking them to monitor it, they're going to change it to what they think it's supposed to be, right? And in the end, they're going to see that there's not a right thing to do, and there's no way to match that Paleolithic diet, and we're kind of stuck. And then we get into all these great discussions about mismatch and, can we ever actually be like our Paleolithic ancestors were, okay? So it sets up a real different kind of dynamic for the students, all right? Okay. One last example that's not an exercise. okay, for my group that is not teaching actively, okay? Teaching is active, learning is active. Learning has to be active, right? We all struggle with concepts sometimes the first time we hear them or for a while. And what often happens is you have this critical moment where a light bulb goes off and it's, oh, I got it. I got over the hump. Something was preventing me from understanding this, and suddenly it clicks, right? Okay. So for me, I had an aha moment when I was first a student. The first time I was ever exposed to concepts of kin selection, things like that, I didn't know how to compute degrees of relatedness. I had never thought about it before. I wasn't a biologist. I didn't do any of this kind of stuff. And so the professor was just going on with information about kin selection issues, and I wasn't following because I couldn't compute the degrees of relatedness, and I was really stuck, right? So I went and asked for help. And when they explained it to me a certain way, when I went for that extra help, it clicked in my head, and I got how you compute those degrees of relatedness, okay? What helped with that insight? What helped? Well, in that particular case, you know, it could just be someone saying it a certain way. It could be a certain example that resonates particularly with a certain individual. Right? But there's something that happened that allows that click to happen, right? That particular example that I just gave you is really interesting because not so much longer after that, I went to graduate school and started teaching this stuff myself as a graduate student. And I went in and was dealing with my class and talking about kin selection, and they were completely lost. They weren't getting it, and I could read that from them. So I went to my mentor, and I said, God, I don't know what I'm doing wrong. They're not getting this. And he said, you know, look, you got to say it this way. And he explained how to say it. And I went, oh, yeah. When I first dealt with this, that's exactly what straightened me out. Like it had left my consciousness. Guess I just figured, you know, I must have been a little dull on that point. And my students certainly weren't that dull. They would get it easily. I didn't need to say it that way and be that basic with them, right? Well, in fact, I did need to be that basic with them, okay? And my mentor said, you know, no, go back next class and do it this way, and they'll get it. I went back next class. They all got it. It was really easy. The funny thing is that the same exact thing had happened to my mentor when he first taught it. And he had gone to his mentor who said, oh, come on, Steve, you have to do it this way. Use these words. This is how it works. And guess what? He did, and it worked. And you know what the funny thing about that is? When Bob first did it, the same thing happened. Okay? There's something about that way of saying this particular set of content that allows people to get it. Okay? So what's the important point? Educators learn from educators, and we have to talk about issues of teaching and how to do it. We have to talk about issues in learning and what works and what doesn't. We have to share these experiences. Okay? So now when my graduate students go to teach this content, I say to them all the time, by the way, Craig, when you walk into that room, I want it done this way, and here's why. And they'll get it. Okay? And they do. All right? So my non-teachers, over here, your assignment, I'm going to have you get yourselves in groups of 5 or 6. Okay, 5 or 6 people. Each group is going to produce one document, all right? I want you to pick a topic or an issue that was difficult for you to get, something that you struggled with a little bit until it clicked, all right? I want you to think about what happened that helped you finally have that click, what made you get it, what was that aha moment, and how would you explain that concept then to a patient, to, you know, another professional who you talk about evolutionary issues with, to, you know, some other person in a way that they aren't confused in the way you were confused initially, okay? And write a little explanation to share that. because how we learn, what helps us learn, is really important to understand. My professor teachers over here, okay? First off, I think folks who are teaching medical students may have different sets of learning exercises that work, all right? So I think folks who are teaching medical students, I'd like in clusters with others who are teaching medical students, okay? I want you to pick a topic that you've either already taught or that you're going to be teaching in a class where you can incorporate evolutionary ideas. And I want you to think about an interactive or student-centered exercise or activity that could be used to teach that concept, okay? You know, some teachers like wikis, some like blogs, some design exercises like I just showed you. There are all sorts of creative ways that you can tie this kind of information to individual lives and get that kind of deeper understanding. So I want you to design an exercise of some sort, okay? You might not be able to do an 18-page document like I have up here for you, but some outline of an exercise that you can do that you think would help get that deeper understanding from your students, okay? And what I'm going to ask you to do is, in both groups, if somebody has a computer in the group, try to type up an actual document. And we're going to send them to Mike McKernan, and we're going to put them on this website and make an archive of interactive exercises and insights into learning particular topics that we can share as teachers and people who are ambassadors spreading proper understanding, deep understanding of evolutionary ideas. Okay? Everybody understand your task? You guys split up into groups of 5. My folks who are teaching med students, groups of 5. My non-teachers, groups of 5. And your instructions are up here in 2 columns. Okay? You're going to report back out, and the faculty here are going to give you some feedback about the things that you design, because we've been working on designing things like this for a while ourselves. So we'll talk about them. You have 20 minutes. 20 minutes.
We had a miscellaneous. I'm a clinician, but we also had teachers and some students. So we had a miscellaneous group of people. And, you know, though a lot of us didn't talk about a specific aha moment, I think one of the things that impressed us about using this as an explanation was the use of, number one, finding a lot of bad examples. So one of the concepts that was hard to get at times, but through a lot of different bad examples came out, was the whole idea that all these things we're talking about have to go through, I guess what I call a keyhole of reproductive fitness. If it doesn't confer a reproductive advantage, then you can talk about, you know, somebody being bigger or somebody being faster or somebody doing certain things or having certain characteristics, but if it doesn't confer that advantage, if it doesn't get through that thing to the next generation, then it doesn't count really as a concept that we'll talk about as an evolutionary thing. And I think that, you know, in discussions with different people, when people would say, oh, I think this is a reproductive advantage, or I think this is is caused by evolution, you know, if it doesn't get through that screen, if it doesn't get through that thing of, okay, well, how does that allow you to have more progeny in the next generation? If it doesn't get through that, then it doesn't count. And I think that helps us to explain to other people by initially starting off with the whole explanation of genes first. So what we are is a product of our genes, but if it's not in the genes, it's not going to be there in the next genes. And so whatever advantage we have, if it's my ability to read German or something, that's not an advantage genetically, because it's not going to be converted to the next generation in a gene. You know, there's cultural parts that we can talk about separately, but that whole idea that whatever example you talk about, and I think that that doesn't get as much play as far as as a concept until you have a lot of bad examples of things that people think, oh, this is a great idea, this is a great idea, this is a great idea, and then you kind of, well, can it fit through there? And they say no, and then say, well, that doesn't count then. You have to pull it back. So you always have to get back to that thing where it has to constrain itself to that. If it doesn't constrain itself to that, it doesn't pass muster. And I think that's one of the things that kind of impressed us. We had other things as far as other people who are new to this understand the whole idea of mismatch, where the genetic thing is staying the same, but the environment is shifting out from underneath, and so that's why you see things that don't look like you're not adapted to it, but you're adapted. It's just the environment that's changing. But this whole idea that it has to be to go through that keyhole, I think is a prime thing that we understood. So bad examples is a key thing. Bad examples that sound really great, but then when you look at them closely, it doesn't fit.
When you encounter misunderstandings like that, at least the thing to think about might be how you can use what Steve Stern put on his slide way back at the beginning of the course about the mechanism of evolution, variability, have to have good terms of introduction, like how does evolution work? What's the mechanism by which it works? And does this actually mutate the material or not? And it's not helpful to me that kind of introduction.
That's great insight. It made me think that you could design an exercise very much like the one Randy had us do at the beginning of the course, where he asked us to decide whether an explanation was evolutionary or not. You could do a similar exercise where you say, does this confer an advantage in reproductive success or not? And you could run through a whole series of bad and good examples and see if people could realize why some fit through that filter and some don't.
I'd like to hear some bad examples. Olympic athletes with vasectomies. Others? Bad examples of fitness. Olympic athletes with vasectomies. Are they very fit? No. Yeah, the vasectomy is done in their toe. They can't contribute genes to the next generation. That gets at the difference between physical fitness and evolutionary fitness. Who is more fit, an Olympic athlete with a vasectomy or an immigrant mother with 8 children who has tuberculosis? Right? The Olympic athlete is less fit. Right?
We don't need vasectomies, right?
Yeah, but you can get fat later, right? Other bad examples of fitness? Did you guys run into any?
I always run into it, but I never think they're bad at the time.
Yeah.
So the diabetes, I don't really know about it. I presented that to this one on California as an example of athletes who really like to exercise in their environment, and I was thinking like, I was here,
All right, we need to move to the next group. Who wants to go next?
Ask a question quick. The evolutionary biologists comment on the term telio, which is thrown out way too much. And I got nailed 10 years ago for using this ridiculous teleology. It's thrown around way too much.
I think we need a little history of science here, and since Bill asked the question. In the early part of the 20th century, the rise of reductionist materialism and experimental science, driven by the German tradition coming into Johns Hopkins and other places and spreading from late 19th century, early 20th century, spread across the country. And at that time, the vitalist tradition in evolution was pretty strong. And by vitalism, I mean that people felt that there was an inner driving force in evolution that was directed towards long-term goals. Books were written by Catholic philosophers like Teilhard de Chardin, talking about the omega point towards which evolution was directed. There was a strong element of mysticism in this. And in reaction to that, people who thought of themselves as rigorous experimental biologists rebelled against that kind of thinking and labeled it teleology. Okay? Teleos in Greek meaning goal, that there was an inner goal in evolution. And that labeling of evolutionary thought seemed to kind of have a superficial plausibility because evolution is capable of talking about how well organisms are designed, and evolutionary biologists among themselves, although they know there is no goal to evolution, and although they do know that evolution is just working with whatever variation is currently available and cobbling it together to get stuff into the next generation, and that it can't look into the future. And George Williams was very good at pointing this out. Even though they know that, they talk about stuff like how well-designed things are, and they are often putting themselves in the shoes of genes or organisms and talking about what would be the best thing to do and stuff like that. This is misleading language that evolutionary biologists use, and it reinforces the impression among outsiders who don't know the local shop talk that in fact they're teleologists. And they inherit that tradition, which is actually quite strong, especially in experimental physiology, that teleology is a no-no, and you shouldn't do it. So I think that there needs to be a lot of discussion of this, and actually I think a rehearsal of the history is a good thing in this context, because the libel, seeing teleology as a libel, as indicating bad science, actually was a good corrective measure between 1890 and 1930, and is a mistake now. Because, in fact, evolutionary biology has become a much more internally, logically rigorous science, and it is capable of talking intelligently about how natural selection designs organisms for reproductive success without meaning that they're going off in any particular direction or that evolution is trying to predict the future. Okay? So is that helpful?
I just want to make one comment. This issue of metaphors is quite common in biology. Evolutionary biology hasn't been the only science confused by it. Look at molecular biology. Words like blueprint, programming, lots of words have got misused, and Lenny Moss, the philosopher, once pointed out molecular biology has become dominated by the person whose metaphor was successful, not whose science was successful.
We like to think of ourselves as lifelong learners, but we agreed that a picture is worth 1,000 words. So that seems awfully extravagant, but um, we we, uh, uh, we agreed that.
You keep talking. Oh no, you have a.
Hold the microphone where you can. Hold it where you can talk to it. That's a little low.
Is this so we had we agreed that the shifting balance theory was sort of hard to comprehend, but a simple graphic really assisted. And the graphic is a contour map where combinations of genes are shown on the X and Y axis, and fitness is shown on the Z axis.
You want to put this down here?
Yes. Thank you. Now we have to assume that this is.
There we go. And you can just scroll down to bring it up on the screen.
Yeah, this is just by looking at a graphic, that helps us kind of get the concept. And I think that's true in a lot of learning situations, is if you have sort of not just a graphic flashed in front of you, but if time is taken to walk through a graphic, that it's very helpful from a learner's perspective to get a concept.
Any feedback, Carl?
Just kind of one quick note about all of this is that the shifting balance is one specific mechanism that you would propose by which you would shift from one adaptive peak to another. And more generally so far is discussed, and we didn't discuss, because the shifting balance theory is quite complicated. It's still an open question. Some would say resolved in negative, whether or not it's an important biological force. But you know, the general concept of peak shift that you're describing here and how you cross the fitness valley, I think is something that's hard to understand until you lay it out like this, and then the diagram can be very
Yeah, and the diagram, if you look at it, it's really highly generalized. I mean, you know, it's almost like a cartoon. It's highly simplified and so forth. But I guess the point we agreed on, from a learner's perspective, it gives you something to discuss around.
right.
Now, can we make sure whoever's speaking has a microphone, so that otherwise the people on the film will not see anything, hear anything?
Oh, I'm sorry, it was the film, yeah, okay.
Okay, actually, Peter wants to respond, so let's hand this to Peter for a minute.
I think it's an excellent point, and you know, I don't know how many times talking with my own students, people say, "Oh, I'm a visual thinker," or you know, it really helps me to when a concept can be presented visually. I think it's not unrelated to what we were talking about before about metaphorical thinking. That often the reason so many metaphors and so much metaphorical language creeps in to our science is because it's a very powerful way of communicating ideas. It's dangerous sometimes because the metaphors aren't perfect and they can mislead, but I think if you look at good science reading, the folks who can find a really good metaphor or a really good picture for something are the ones who can convey it and produce perhaps more of those aha moments.
Selfish gene being the ultimate example of both success and failure.
Right. Yes.
I want to add something to that because I think the visual representation is great, but I'm often running during talks into issues where we would be presented with a great figure or a great graph, but shop talks we call them, shop talks, like on
Yeah,
the
yeah.
talks, I find that even much more efficient than presenting us with loads of graphs and on nice presentations, fancy and beautiful, but I think really to get the message through is to go to the whiteboard and move the student to the x-axis, the y-axis, and draw it.
I have
The
a
explanation is
I have the pleasure of teaching a course on evolutionary anatomy and physiology with 3 colleagues. 3 of us do wonderful, do PowerPoint presentations and all that stuff. One of us, George Lauder, is a master at drawing on the board, and the students love it, and it really resonates with them, so I agree. Yes, and it goes slower, and you can see the thought evolve as the picture does.
Yeah, I think that's important because it forces the faculty member to explain what the axes are, what the relationships as they're drawing things, they're thinking about, is it the slope of the line or what is it that's important about how this graph looks, and they talk through that as they do it oftentimes, so I think that's very helpful.
I think a way you can almost do a chalk talk if you don't like to write is that the PowerPoints where things come in one at a time, I think are very helpful to me because then I can look at the graph and then you kind of explain what the X and Y, and then the arrow comes in and says, and this is representing fitness or whatever, and then I'm like, oh, okay, that represents fitness. But when it all comes at the same time, I just start getting anxious.
Okay.
Sorry, one last comment.
Yeah, please.
AV glitches can be very useful. One of my courses once, the PowerPoint projector went totally out. The guy came, he could not get it to work, and I said, forget it. And I drew I did the whole lecture, sort of drawing the slides, as it were, as I went along, and the students uniformly said that was the best lecture I gave in the whole year.
We need to move on.
Okay, I just wanted to suggest that the shifting balance theory is something that's mobile, and there might be one way to show that mobility by looking at long-term floods where peaks come up and peaks go down and waters go down. There might be a way to draw that.
Okay. I just want to make a quick comment about the PowerPoint motion. I think as educators, it's important to be aware of what Alan Leshner from the National Institute of Drug Abuse said. He called it PowerPoint poisoning. When he learned PowerPoint and started learning all of those little features, he had slides that had every effect, and they were mixed up every which way, and And he said, I really feel like I have PowerPoint poisoning, and it was one of the worst presentations I ever had to sit through in my life, because you never knew why things were moving, what was going to move next, and it was really distracting from the content. So I think intelligent, meaningful use of motion is really great, but be real careful. Okay, next group.
Thank you. I'll stand over here so my back won't be towards anyone. I represent the group that focuses on teaching medical students, but this exercise we talked about can really be pitched at any level. We seeded the discussion with an exercise I'm currently doing with only limited success to third-year medical students, and the group really worked to improve that. Basically, one would either by assignment or have the student identify a disease or disorder or patient they've encountered during their experience and answer 4 simple questions. What is or are the biological contribution to that disease or disability? What is or are the ecological contribution to the disease and disability? And by ecology, we would mean microecology, sort of current living environment, or macroecology, what's the geographic ancestry, flora and fauna, so on and so forth, for the geography of origin. Third question, what is or are the cultural contribution to the disease or disability? Now, my original exercise would stop there, hoping that the student would, when they consider these 3 factors, is thinking evolutionarily without the word evolution at all. The group suggested that there should be a 4th element, which is 4th question, and make it more clear, which is that how do these factors came to be over evolutionary times, to sort of spell it out so one knows what the expectation is. And that the final exercise component is that as a future physician, how do you modify one or more of these factors to bring the student back to a state of health, whatever that means. So the group thinks that providing specific example would be very helpful, so we came up with either very simple disorders, if you call it that, such as albinism. The biology is clear. Or if you want to soften that up, skin pigmentation. The biology is clear, and the ecologic impact is very clear. And also, well, some of them may not be so clear. And also the cultural reaction to folks with different skin color in sort of cultural selection sort of sense is also very interesting. Or to vary it in a less rigid disease model, what about coronary heart disease, asthma, alcoholism, and you know, other examples.
Okay. 2 minutes, questions, faculty feedback, ideas.
One of the great challenges in teaching doctors in general is to help them realize that there's not one cause for disease. I mean, in medicine in general, people are always trying, the cause of even pneumonia is the pneumococcus. Well, of course it's not. There are all kinds of things going on in that individual that make that individual vulnerable to the pneumonia other than just being exposed to the pneumococcus. I think this is a great challenge of teaching. But are we trying to get students to explain why this person has a disease, why this individual is different from other individuals? Or are we trying to get them to explain why humans in general are vulnerable to this disease? Or should we do both?
Well, we did not really address that. The original idea of the exercise was the student to start from a patient they've encountered. So this connection with, it's my observation. But that currently could be extrapolated at a population level.
We teach evolutionary medicine on a case-based approach in Auckland. We start with formal classes which are based on cases which we've devised which illustrate specific points. We usually start with scurvy for a variety of reasons. It teaches about phylogenetics, it teaches about neutral mutations, it teaches about mismatch, has a lot of points in the and it's not threatening to the students because it's something that none of them have seen. So it doesn't put any of them in an embarrassing position. what we're now trying to do is introduce, and that allows us to teach about proximate and ultimate causation and then the various pathways involved. What we're now trying to do is then immerse within a changing curriculum where a lot of the teaching is going to be built around cases, but as well as teaching about all the proximate and models of causation, which are just both biological, sociological, and cultural, that the ultimate explanation should be part of that discussion as well. And so finding the right cases to make the point clearly is quite a challenge at the start of the course, but it's important.
Okay, thank you. Next group.
I was with a group of clinician teachers who all were focusing on teaching house staff, that is, medical residents and fellows learning in a hospital clinical setting. And we lit on a topic that we think gives us the opportunity to teach about a number of evolutionary principles, including the proximate evolutionary distinction, trade-offs, mismatch, and probably something else that I'm forgetting at the moment. But the seminar is called Scared to Death. It begins with going around and asking every resident in the room to describe a situation that they remember being the most frightened in their lives, to briefly describe that. And we follow that by a case description of a middle-aged woman who comes in holding her dog that was just run over by a car, and she's clutching her chest. And it's a case of Takotsubo cardiomyopathy, which is an acute stress adrenergically generated dilatation and weakening of the apex of the myocardium that can be fatal. So with that case, we have the opportunity of talking about the trade-offs, signal detection theory, and mismatch. I'm not going to go into the details of how we might do that, but the idea would be that we would be case-driven and have that case kind of, you'd start in the normal way of saying, how did this happen to this woman? How do we understand it? And of course, the discussion is all about proximate pathophysiology. And then you turn it around and you say, so how is it that her body was left vulnerable to having this happen to her in the first place? How do we understand this evolutionarily? And that opens up the door to a discussion of the principles that I mentioned. Now, and if we can get a clip from its great Twilight Zone episode, we would use that too. Who could describe it very briefly? It's the guy on death row who is led along and eventually.
A newspaper reporter on death row to see what it really feels like to be on death row.
Ah, right.
Editor arranges for his number to be changed, so that everybody's now acting like he's really on death row. Gets up to the point of execution and gets scared to death.
And you pull the blindfold off and he's already dead before he gets into the chair, that's the idea. So I'll stop there. I don't know if anybody else in the group wants to add anything or see what questions people have.
I was just going to, one of the points to take into, I think, was also not just in this acute setting, but how this type of signal issue relates to a broad area of other health issues, from psychology to reproduction to various other issues.
Right, the impacts of chronic stress. So, feedback, questions? Peter.
Only to make a point back to the first of the presentations, here's an example where you're using evolutionary principles, not to talk about fitness, but to talk about clinical syndromes. So I think we've got to be careful when we think about evolutionary medicine that we're talking about a broad range of topics beyond just fitness for fitness's sake.
We had a great discussion about pre-predation.
Wait a second until you get the microphone.
Oh, I'm sorry. We had a great discussion about pre-predation, which that is that this massive catecholamine overreaction might it was a signal to noise discussion about where, under what conditions evolutionarily it might have been appropriate to have a massive catecholamine release to avoid predation, and that was one of the things that we talked about.
Thank you very much. Oh, Jillian.
This isn't directly related to what Mark was saying, but I did want to just have the opportunity of mentioning a strategy that I've taken in my teaching before. And when I first started to teach evolutionary medicine in a class, which was primarily in an anthropology department, and it covered both graduate and undergraduate students, because that's just the way it was run at the time. When I first started to think about designing a class, given my background, I thought, how am I going to deal with this? There's so much that I don't know enough about, and there's always the risk when you're teaching a class of being overtaken by your students, which is pretty scary. So I came up with a strategy which was high risk, but it actually worked fantastically, and Randy participated in this a couple of times, where I invited people into the class and I interviewed them. Like Oprah Winfrey, I kind of set up the room, the classroom like this, so we had chairs and tables with water and stuff, and the students were invited to participate in the same way that Oprah Winfrey ran her chat show. And sometimes I would have 2 people in the class, and that was absolutely fantastic. So on occasions, I invited an evolutionary biologist in to say, if it was called, talk about coevolution, host pathogen, or something like that. Or I would invite in a medical doctor. And when I first started to do this, I thought every medical doctor is going to say no. I really thought that nobody, given what they do, how busy they are, that I had no money to pay them any honorarium, that I would just get no's all the way around. I never had a single clinical doctor, this was in London at the time as well, who ever said to me no. Sometimes I couldn't make the dates, but they never said no. They were thrilled to participate in this endeavor. And then on other occasions, I would invite a clinical doctor in to discuss something from their clinical perspective, and an evolutionary biologist. So one time I had a paleoanthropologist talking about the evolution of bipedality, and an osteopathic doctor talking about lower back pain. And so the students were able to ask questions. It was really participatory. It saved my neck, let me tell you, to do it that way. And then we started to videotape these interviews. I did get a little bit of money to do that, so we do have this little archive, which is really interesting, that I hope we can get. It's complicated now because I've moved institutions. There's all these legal issues going on, and who's got copyright of this, et cetera, but we do hope they'll have this resource up, for students in the future. But if you are thinking of, doing a class or teaching, it's a wonderful way of approaching issues and getting students to be thoughtful and ask questions, and they loved it. I loved it too, so.
Excellent. What a great idea. We ready?
Okay, so we're actually, we're all teaching very different groups of students from high school all the way to graduate school. And so we were trying to integrate some topics that we teach in various ways. And so we thought about the topic of osmosis, osmoregulation. And so the idea is that, and I do this to some extent with my students, which is mostly undergrads. So I do ask them actually, the first question would be, so you go out to sea and you're trying to survive, you get thirsty, but you're not supposed to drink seawater. Why? And it's actually that fact most people know, but the reason for it, I rarely get any good answers initially. So what I have to have them do is actually come up with hypotheses why that is actually a problem. And I got quite interesting answers to that before, anything from clogged salt glands on the tongue to all sorts of other things that are really bizarre. So I have them come up with hypotheses, and that is already sort of a good exercise. And then we're going to start talking about, why this is. And at that point, I would introduce things like, osmoregulation, osmosis of cells. And once we have this all established, then I would ask them, is it also a problem, the opposite of it? So if you get too much pure water without salt in a short period of time, is that a problem? So basically, could you kill yourself by drinking distilled water, lots of it in short periods of times? And there's actually records in the literature that you can. And so we get also to, why that is, why humans have, a rather small range of what they can tolerate. So it has evolved in this way. And then we're going to get into the points of what can, in what kind of situations where organisms live would you expect some other strategies that have evolved to get, say, rid of excess salt. And so we have discussed some examples of anything from a desert animal that has less water available, but you also have those things of, say, a whale being a mammal going back into salt water. And so there's lots of potential strategies. So a lot of that, when I do that, is because I have 40 people in a lab and no TAs, is that I get them in a computer lab and have them do research. And along the way, also tell them, good sources to find information and things like that.